In this video, we will understand few basic memory formulas and your catch formulae so that it will be useful for you in order to work on with your mapping techniques, right? So, to start off with, let us consider main memory which contains 128 bytes. So, 128 bytes are represented in all these locations, okay, in these locations. For understanding purpose, I have taken the size of the main memory to be small, which is 128 bytes. So, each and every location of the main memory is addressed, right? So, the first location is addressed 0, 1, 2 and so on up to 127. So, totally we have 128 bytes of memory. Hence, we are addressing it from 0 to 127. These are how we will be assigning the address. So, the first location is given the value of all zeros and last location is given the value of all ones. Binary representation of the address is like this. Instead of 0, 1, 2 and so on, we are using binary values because memory address are always given in binary. Now, when a processor wants any data, it will be asking the memory only in the form of physical address. Yes, so physical address could be written in the short form as PA. Now, we will understand how many bits are required for the physical address. For that, we have to consider the memory size. Memory size here is 128 bits. So, which is nothing but 2 power 7 bytes. So, we will take this value 7. So, totally it requires around 7 bits. So, the physical address is 7 bits. That is why we have 7 zeros here. Yes, and these addresses are 0 to 127. The last bit is all ones. So, you have 7 bits here for representing the physical address. So, for a memory with 128 bytes, 7 bits are required for the physical address. Now, we will go on with the other things. We have the cache, which is in between the main memory and the CPU. Cache is being used because the processing speed of the CPU is high when compared to the main memory. In order to have a balance, strike a balance between the processing speed, we have introduced the cache. But it is not going to be of the same size as your main memory. We will have only the capacity of the cache is going to be less when compared to the main memory. So, whatever data is required by the CPU will be transferred from the main memory to the cache and then to the CPU. This is how it will happen. So, let me say if CPU is requesting for this block, right? CPU is requesting for this block. What will happen is that block will be transferred to the cache and then to the CPU. But in reality, only one block will not be transferred. Instead, the many number of blocks will be transferred, and this selection of block is based on spatial locality or temporal locality. They are called as locality of reference. So, based on the applicability or based on the future request, it will be prefetched and stored in the cache. So, that prefetching is based on spatial locality or temporal locality. So, here the nearby blocks are transferred to the cache and only the second block is requested, so that alone is transferred to the CPU for processing. So, we will consider the block size as 8 bytes. Okay, so this block will have 8 bytes. Similarly, the cache will also have the capacity of 8 bytes. Each block in the cache will also have 8 bytes. Though the size of cache is small, each block contains 8 bytes. It is going to be same for both the main memory and the cache memory. For understanding purpose, main memory is represented in the block addressable format. So here we have 0 to 127. That is why it is represented, because the block size is 8. We have 8 bytes here and 8 bytes are arranged in each block. Okay, so totally it is represented by this. So each is a block. Memory block is 8 bytes. So in each row you have 8 bytes. Totally we need 16 rows for representing this 128 bytes. We will see how it is being calculated. So the number of blocks, how many blocks we need, that is the number of rows we need, right? It has to be stored in the rows. So for that, number of blocks NB is calculated by the formula. It's a ratio of memory size divided by block size. Here your memory size is 128 bytes, okay, and the block size is 8 bytes. So it is 128 by 8, which is 16 blocks. So we have 0 to 15. Yes, we have 16 blocks here. Number of blocks is 16. And this is called as block index. This is called as block index. We will not be using 0, 1, 2. Instead, we will be using the binary address. And because we have 8 bytes in a block, the columns are numbered from 0 to 7. So it is called as, this is called as your block offset. This is called as your block offset. Yes, so here we have 16 blocks. So it is numbered from 0 to 15, but internally it will be represented only in binary. And then the columns are called as block offset, where we have 0 to 7. Because it is 0 to 7, only 3 bits is enough. So it is 0, 0, 0 to 111. Okay, so in order to access 43, for example, if we want to access 43, the address will be 0, 1, 0, 1 and 0, 1, 1. It is nothing but your rows and columns. So 0, 1, 0, 1, 0, 1, 1. If the address is this, the value that is the block that will be taken is your 43rd block. Okay, so let us consider here. This is your physical address. So this is the value given. Now, because the block index is 4 bits, we will be dividing into 2. So it is 1, 0, 0, 1. So where do we have 1, 0, 0, 1 here? Yes, this is the line. Then 0, 1, 1. So 0, 1, 1 is 0, 0, 1. Sorry, 0, 0, 1 is here. So the intersection of this row and column is 73. Hence, this 73rd block is retrieved. This is how you will be retrieving, and this is how you will be calculating the physical address. Okay. So the last 3 is your the second half is your block offset, because 3 bits represent a block offset, and this 1001 is your block index. Okay. Yes. So this is how the physical address is framed. For understanding purpose only, we have taken 128 bytes, but in reality it will be more. So the physical address contains first n bits, which is your block index, and the last n bits, which will be your block offset. This is your least significant bytes, okay, and this will be your most significant bytes. This is how the physical address is calculated. And this block offset depends on the block size. In our example, we have used 8 bytes. Okay, so the number of bits of block offset depends on the block size, and the number of bits in your block index depends on the number of blocks. So this represents the rows and this represents the columns in your block addressable memory, because you have represented a block address memory. Okay, so let us see one more example. Now if we consider the main memory size as 64 bytes, it is 2 power 6. So 6 bits is needed for your 6 bits are needed for your physical address. Okay, and then the block size is 8 bytes, which is nothing but 2 power 3. So block size is your block offset. Block offset depends on your block size, we saw, right? So the block offset is 3 bits. So this will be your block offset. Now what will be your block index? Block index is dependent on the number of blocks. So we want to calculate the number of blocks. Number of blocks is nothing but ratio of memory size by block size. Memory size is 64 bits. Here we have 64 bytes, and divided by your block size is your 8 bytes. So 64 by 8 is 8 blocks, okay, and it is 2 power 3. So totally we need 3 bits. So this will be your block index. The first 3 bits of your physical address will be your block index, and the next 3 bits will be your block offset. This is how you can relate your block index and block offset to the physical address. Yes. Now we have learned few formulas that were related to the main memory. Now we will see few other formulas which are related to the cache memory. You have to understand all these formulas thoroughly so that you can easily work on problems when given in the exam point of view. And also all these problems and formulas are very important from the gate perspective, okay. So now we will consider the same scenario. Here we are using the cache memory. As I have already told, cache memory is going to be less in size when compared to the main memory. For simple understanding, I have used the size of cache as 32 bytes, okay. So it is addressed from 0 to 31. Yes. So as we have calculated for main memory, we will also understand how it is calculated, okay. So 32 bytes is represented in the form of 2 power 5. So totally the number of address in your cache address, number of bits in your cache address will be 5 bytes, okay. Now this is your representation of cache, okay. This is a representation of cache. Here, as I have already told, both the main memory and the cache memory block size will be same. So in this example, I am taking the block size to be 8 bytes, okay. 8 bytes. This is byte addressable, okay. Each thing is representing a byte. So you have 0 to 31. So 32 bytes are your cache. So we have represented this cache memory in this form. So number of blocks, because this we need to know the number of blocks, right? Here, because it is cache, we will use CS, cache size divided by block size, which is nothing but 32 divided by 8, which is 4 blocks, okay. Because here in cache also we are referring to as blocks, you will get confused. So I am replacing this block as lines. So total number of lines is 4, okay. You have 4 lines here, that is 4, you have 4 rows here, okay. You have 4 rows. So it is line 0, line 1, line 2 and line 3, okay. Now as we have calculated the block index, now we will be also calculating the cache index, okay. So before calculating the cache index, we will also calculate the block offset for the cache. So here the block size is 8 bits, right. So it is 2 power 3. So the block offset is again 3 bits as your previous memory example. Now it is also same, and I've told, right, your cache size is 32 bytes, which is nothing but 2 power 5. So your cache address is 5 bits in length. Now we will see what is how CI, that is nothing but your cache index. As we had block index there, here we will call it as cache index. So how many number of lines are there? We have 4 lines. So it is 2. We have 4 lines. So it is 2 power 2. So this 2 bits are required for your cache index, okay. So your cache address is nothing but block offset and your cache index. So totally you have 5 bits. So it has got tallied. Yes. See here, your cache address has your first part, which is the most significant part will be your cache index, and the least significant n bits will be your block offset. This is the cache formula. Hope you would have all understood how to calculate the size, okay. So given few inputs, you will be asked to calculate all these values. We will see few examples in the upcoming videos.